So my name is Sascha Hunold, and this is joint work with Klaus Kraßnitzer. And we are working here on the OpenMP task runtime systems. And we are both working at the Vienna University of Technology in Austria. So what are we going to do here? So I have some mic here in my ear. Can you turn off the mic, please? Would it be possible to turn off the mic? Whoever has a mic on. Okay, so we are, I mean, a very brief introduction because we are dealing with OpenMP. So OpenMP is a standard for programming shared memory systems. Most of you will know. And the idea is that OpenMP provides these compiler directives, aka pragmas, in order to make sequential code parallel. So we insert these pragmas, and the compiler takes care of parallelizing these bits of code. And OpenMP supports the following languages: C, C++, and Fortran. And what we usually find is two ways of programming with OpenMP. One is the traditional data parallel way, where we have a loop, and we are trying to parallelize that loop. And basically, each thread gets assigned a chunk of that loop, if the loop is parallelizable like that. Or the other way is if you have a more irregular application or a recursive call, like something like that, if you want to traverse a data structure like a binary tree, well, then this traditional data parallel mechanism will not work. And this way, in this case, you can use these OpenMP tasks. So for example, if you go in there, you create a task, and this task will be given to one of the threads that will be available. And in this way, you can express your parallelism in a different way. And in this talk, we are primarily talking about task parallel applications. So what are the goals here? So all these modern compilers nowadays, they implement these OpenMP runtime systems. That's what they have to do. So the question is, how do these current OpenMP runtime systems found in these modern compilers like Intel's ICC, GNU's GCC, Clang of LLVM, and NVIDIA's PGCC, how do they compare in terms of parallel scalability when they are presented a large number of independent tasks? That was just the idea here. And of course, we had some hypotheses that some of these OpenMP runtime systems that have a central data structure like libgomp of GCC would perform significantly worse when you have a lot of threads compared to the ones that have multiple queues like libomp of Clang, and especially because they also support work stealing. And what do we do? Well, it's a bench conference. We implement a benchmark that can help us to assess the parallel scalability of these runtime systems. So our contribution here to this conference is this OMPETB benchmark suite. And what does it do? So you can check it out here on this link on GitHub. It's a benchmark to assess the scheduling performance of OpenMP runtime systems. And what we took care of is what we call compiler fairness. So the work that is done by each task is compiled with the same compiler, but the rest of the program, the benchmark itself, is then compiled against the actual assessed compiler. So we can the instructions that each function is doing are the same, but they are implemented, they are executed by a different runtime system that depends on the actual compiler. And we support homogeneous and heterogeneous workloads. And what is also unique to this one, we also have profiling and tracing functionality in there. So profiling, you often would like to know if you have a lot of threads, how many tasks were actually executed per thread in order to know whether it's load balanced or not. So what are different strategies? I mean, there are some strategies that have already been proposed before. And one of the strategies that we looked at is the so-called master task strategy that happens often in applications, where we have a parallel application, like a parallel block. So we have a lot of threads are spawned, but only the master thread here, this master thread creates the task. So the master thread is here, it's only one, and all the tasks in that loop here, in that for loop, are created by that master. And how many tasks do we create? We exactly create n tasks, so that's one variable in order to vary this number. How many do we get? Oh, sorry. And also, we need to know how much work is done by each task. And I give that work here as we call that Tbench. It's just a simple function that has a runtime of O of m, so it's linear in m. So we present it in m, and we get some kind of work done linear in m. And what we can also do is, if we have this heterogeneous workload, this m is varied every time we access this work function. So we have two other task creation strategies. One is where it's not only the master thread is creating the task, but all threads create the task. So we basically exploited OpenMP for functionality, but in that loop, we create tasks. So each task, each thread, we have p threads, and each thread creates one piece of the workload in parallel. So we have a lot of tasks created by all the threads. And as a baseline implementation, we are using something called the parallel for approach, where we don't spawn any task. We just execute the same work, either heterogeneously or in a homogeneous setting, just by executing that for loop, which is then some sort of baseline implementation, and it's this performance baseline in order to compare how much overhead we have with these parallel tasks. So we try all these kind of things on different machines, and the interesting thing is that we have different architectures, we have Intel architecture, we have AMDs, and we have also AMDs of different generations, and all of them are dual socket machines, which makes things interesting, whether they scale these tasks scale across several sockets. And in total, the compute nodes that we work on have either 32, 64, or 128 cores. And you see the compilers that we test, they were fairly, I mean, the newest ones, most of them back then when we wrote the paper, but they're still fairly recent. So on the Intel architecture, we're using the ICC, and on the AMD architectures, we also include the AOCC. So what are the results of our experiment? So the first experiment is a homogeneous experiment where we create 100,000 tasks, and each task is very small. So basically, we would like to really assess the scheduling performance of that system. So we basically stress that system. Each task has basically no work. It's done in no time. And we also do a strong scaling analysis here. So these are the cores. This is the time in seconds. And then we see the different bars denote the different compilers. So orange is Clang, green is GCC, ICC, PGCC. So the first thing is they don't scale at all. So what you would actually like to see is that the runtime goes down the more cores you have. But in this kind of scenario, when only one, if you have this master task pumping in tasks there, then it basically doesn't scale well. And you see that GCC already with 4 cores will take a performance penalty here. And also ICC with 8 cores already starts slowing down a lot compared to the other ones. And what we also compare is here, there's the compact and scatter mapping that basically just means how we assign the threads to the machine. Either we fill up one socket, or we do a round-robin assignment of the threads to the cores in the scatter setting here. And we can do that for the master task and for the parallel task. So for the parallel task, you see that's much faster already, although GCC takes roughly compared more time than the other compilers for a few of these core numbers. And here it looks like it's scaling a little, although the time it's a different scaling. So they're probably more or less the same. But the thing is, in this kind of scenario, they don't scale well. It's not expected, but you see huge differences between these compilers. That's what we didn't expect. And so it was also not surprising to see that this master task strategy doesn't scale well. That was already found by Terboven et al. And but we found somehow that the mapping strategy, there was no clear winner. In each case, it was different. On homogeneous on the larger AMD machines. So we start here with 48 up to 128 cores, and we have the different strategies here, master, parallel, and parallel 4. We only use the compact mapping here now. And you see that for some reason, AOCC and Clang with 128 cores are slowing down a lot. Why that is, we don't know. Also, in the parallel task setting, PGCC, which was by far the best compiler overall, here takes a hit for 128 cores. It was significantly slower than the other ones. And also in the purely parallel 4 setting, there's also differences here. You see that PGCC was by far the best. So what our question was, can we somehow predict the performance of the different runtime systems based on performance numbers, whatever we can measure, hardware performance counters or software performance counters? So we asked, for example, does this parallel runtime that we get correlate or inversely correlate with the number of tasks each thread is executing? So here, that's one of these graphs on top. We have the different compilers, AOCC, Clang, GCC, and PGCC. And then on the y-axis, we have the total number of executed tasks. And you see here, each of these bits here represents a core. We just removed numbers because it would be, you couldn't see much there. But the thing is that there's a load imbalance here for the PGCC. And for example, these cores here, they execute many more tasks compared to the GCC. GCC is very load balanced, although PGCC is much faster, and not much, but it's significantly faster. So the number of tasks per core was not a strong indicator here. And the same goes for the cache misses. So we looked at the perf results of the different compilers, and we expected that more cache misses lead to a longer execution time, but that's not really true. So you see, for example, here, the GCC, the first core of GCC has many more cache misses than the rest, and that's also expected because it only has the central data structure, which is stored at core 0. So we have a lot of cache misses here, but overall, the cache misses are very low, and GCC is still faster than the other ones, although this one is higher. So there's also no evidence that there's a correlation there. So I'm almost done. And one particular important thing was looking at heterogeneous workloads. So now we have a lot of tasks that have the same size, the same length. So what if we present the runtime schedule with something more heterogeneous and in a more reproducible setting? So we look at distributions, and especially like an exponential distribution. So we sample from exponential distribution these task sizes, and this exponential distribution is actually a realistic model for jobs in parallel settings, and we can find this here in this related work. But in order to be efficient, we actually pre-sample from this distribution before the program starts, and then we have a lookup table to know exactly in a quick way how large each task is. So for example, this is one that we test on. We have this long tail. Most of them are short and some of them take longer. But the main outcome is here. So this graph shows, again, on the AMD, we have 1 million tasks to run. And these show the relative runtime with respect to GCC. So if you're above this line at 1, you're slower than GCC. If this bar is smaller than 1, you're faster than GCC. But interestingly, we did all this and we couldn't really find a lot. But we found that the heterogeneity wasn't the biggest factor here. We compared the results. This lambda distribution here with 0.02 has a mean of 50, and but it's heterogeneous workload. But if you use the same mean of a distribution, like here in this case, what we always have a distribution with a homogeneous distribution with a 50 fixed workload of 50, then the result is exactly the same. So the mean running time of a task has a much bigger impact on the scheduling performance between these compilers than heterogeneity itself. Okay, with this, I think I have my 10 minutes, and I think, again, Bench 22 for making all this possible, and also the organization committee, and particular the program committee for making this conference nice. Thank you.